All right, all right.
Yes, welcome to Organic Chemistry. I'm Dr. Stevens, Chad Stevens. I'm your professor. Looking forward to getting to know you this semester. It will be a great semester. We have essentially 2 lectures a day, 10 lectures in a week. First test is next Wednesday. But we will begin test 2 material on next Tuesday. Okay, got a number of handouts here. Good morning to everybody. We'll do, I think, 1 stack. Okay, syllabus. Here we go. Just working back, end up over here, yeah. And if you can make sure I get the leftovers. Not necessarily now, but whenever you leave or whatnot. Okay, we'll spin one this way. Functional groups, DUS. Outline. Lecture outlines typically I'll have on colored paper, and green outline here. Y'all like DQ? Got some DQ here for you. And let's do one more. How about that? I usually give this one out a little bit later, but in summer, really get you things ahead of time. The sooner the better, yeah? So if you want to be looking ahead, that will be a good thing to do. Which brain indicates Alzheimer's disease? I can't remember. I don't teach in here regularly. Was it your last summer? I can't remember. We didn't keep one with the lights off. I don't know why this all went off. Didn't help. We may keep that off. We'll have to see how it goes with the handouts. See what looks best. But I don't want anybody falling asleep. Yeah. Don't risk that, do we? How are we doing on handouts? I think we got 5 handouts. I think there's 5. Anybody? How many do you have? 5? Somebody got extras? Where'd they end up at? Got some extras? Just make sure I get them, drop them off up here on the way out, or unless we need them now. By getting 5, I think we got a green one, a yellow one, and 3 white ones. Is that right? That's a good looking compound here, yeah? Organic, what's organic chemistry? Organic chemistry. Typical carbon-based compound. That's super generic definition though. Basically there's millions and millions of different types of organic compounds containing carbon. Many more so than compounds that contain silicon. Do we have a periodic table? Yes. It's also one on the back of your workbook, lab manual. You got a workbook lab manual yet? I put a periodic table on the back of that for you. You're welcome. Anybody not get my emails about the pre-course meet and greet that included a number of attachments and information? If not, please email me and I will forward you that. And discuss things like the workbook lab manual. Periodic table up here. Silicon, right under carbon, doesn't make nearly as many compounds as carbon. Carbon loves to bond, and thus it makes lots of different molecules, carbon bonds to these guys over here a good bit, nitrogen, oxygen, sulfur, halogens. Carbon likes to bond, likes to play, likes to be a good friend. Gets its own branch of chemistry, organic chemistry, hugely applicable. Anybody have a cup of coffee this morning?
Yes.
You had over 1,000 organic compounds in that cup of coffee. Some of them cure cancer, some of them cause cancer. Okay? Beautiful compound here. How many carbons we got there? Line bond structures. Need to be able to determine number of carbons, number of hydrogens, formulas, etc. That compound is used for imaging of the brain, particularly for imaging Alzheimer's disease and the beta amyloid plaque that's formed in Alzheimer's there. Lots of application of organic molecules. Syllabus, yeah? We got to get through some procedural stuff here and we got to get going. So I'm going to run through some of this stuff. There's your syllabus. Information's here. Your first assignment is to read the syllabus and ask any questions tomorrow or sooner or later. Everything is there. Course overview, important dates. Test schedule. First test is when? Next Wednesday. Grading. Everything is here. Everything is to be read. General comments on studying, information, helpful information, requirements, etc. Dear Jane, there's your daily outline. Today we are where? Right here. Lewis structures, functional groups. That's what we're doing. Lab. We have lab twice a week. Is that right? Here's your week. There's 2 labs here. Okay. Today we're checking in, and then we'll have a lecture downstairs. Hopefully this room is available. Okay. We will probably look at IR. How are we doing with IR so far? That's covered by video only. Okay, I sent that IR handout packet in the original email, one that talked about the meet and greet. We used to check in and come downstairs and have big long IR lecture. One shot. Okay, video you can watch it 10, 20, 50 times if you want, anytime you want. All right. Our first lab on Wednesday, Thursday, is that right? Wednesday or Thursday? I'll say Wednesday, Thursday, solubility testing of organic solids. The labs are in your lab manual, the back of the workbook/lab manual. Okay? So there we go. First test. Makes funny, no class. Yeah, there's the test. Okay. Other things, learning outcomes. My background is in medicinal chemistry, drug development. I'll use drugs to illustrate a lot of organic chemistry principles we'll be talking about. Here's a list of some common drugs. You maybe have taken some of these. Like Tylenol. They're all small organic molecules. Okay? But when we look at the structure, we need to be able to see things in that structure. Physical properties, structure, architecture, bonding, reactivity, stereochemistry. Just looking at a structure, that's a lot of introductory organic chemistry. Okay? There's some sort of types of questions you might ask about drugs. Okay? We'll hopefully answer all these as we move along in the course. Okay? By the end of the course, you'll be able to readily answer these types of questions. All right? You'll be then ready to go on to advanced courses and and ask or answer more advanced type questions that are going to be beyond this course, but we're preparing ourselves for the next course or the next whatever you're going to do in life. Hopefully you're here for a reason. Okay? I imagine it's some type of scientific career. Okay? Organic chemistry will be tremendously useful to you. But in addition to that, it's the learning process of how to learn, quickly assess, learn, ask questions, form questions, write questions down, be organized, work ethic. Okay? All these things go into making you a better candidate for this scholarship, for this internship, for this job, for this whatever. Okay? Make you better to be able to be productive in whatever field you go into. So it's more than learning carbocation rearrangements. To me, it's learning how to be productive, focused, committed, willing to work hard to achieve something. Hopefully that's what you're here to do. And then those basic principles will then set you up to go succeed in the next course or whatever. Hopefully more than course. We don't want to learn to be students. We want to learn to be productive scientists or leaders in our field. Do something. All right? So, to me this course is half of content, it's half of the intangible stuff. Okay? By the way, that's the name of this course. I can't quite figure it out. It looks like it's the chemistry of cool stuff. Yeah? Cool stuff. What does that mean? What is that? I think it's Dutch for carbon. They call it cool stuff. Carbon, chemistry of carbon. It's pretty cool stuff, okay? I don't know, maybe I'm just making that up. Okay, any questions at this point? Who doesn't have the workbook lab manual? Okay, information was in the email. Main chemistry physics office, $15 cash only. Those used to be additional handouts. I gave you 5. I did not give you 10 because the other 5 handouts were in the lab workbook lab manual. Okay? You'll find that to hopefully be very organized and a very nice resource. Give you lots of questions that are my type of questions, but they are more intermediate or advanced level questions. The basic questions you need to be working, introductory questions in your textbook. Official textbook is the Klein book. Again, most of this was in the email. The bookstore has a paperback version. Okay, David Klein, John Hopkins. You also need the solutions manual because there's plenty of problems to be working. You need the solutions manual to see how you're doing, to gauge your progress. Okay? I do allow you to use any book you want. Anybody using a different book? Bruce, anybody using a different textbook? What you got? Carrie, okay. Carrie, I think, does 2 different textbooks. Carrie is a good textbook, yeah. Been around a long time. The information is going to be 99% the same as in Klein. Okay. It'll be missing a few topics, but guess what? Klein is missing a few topics that we will cover. Maybe that topic is in your book. Okay. The goal is not to buy everybody have the same $300 textbook. The goal is to use a textbook to work problems. I give you outlines of what topics we're doing. I'm sure you can use the table of contents, find this chapter on the topics we're covering. Okay. Read about it. That author will give you a different version than me, which is good. You don't want the same version. Okay. The more versions you get, the more it's sort of, okay, this makes sense. Okay, oh, I get it now. Okay. Work problems on that topic until you're satisfied and you're ready to go. Okay, lab. You also need a lab techniques book. Again, all this is in the syllabus. The book by Morag is the one of record. We used to use one by Zubrick. You can use that one. You used to find those older edition of Zubrick online for a penny plus shipping, $4 book. In the end, those are going to be books about lab techniques. Again, the requirement is not for you to buy a book. The requirement is for you to come to lab prepared. These lab technique books are sort of the main book that does that. Maybe you have other resources. Okay? And maybe there's some other book. Maybe there's an online something. In the end, if you come to lab prepared, I don't really care what book you have. Right? If you don't come to lab prepared, there are going to be issues. All right? We can't work unprepared in the lab for many reasons, including safety. All right? There's many things I could say today. I will sort of regroup and say some other things tomorrow, and also maybe get questions from you. If not now, definitely tomorrow. The syllabus talks about being organized, writing questions down, okay? Almost like a little journal, all right? See, a lot of students like, oh, I had questions, but I can't remember it. Well, I had 5 questions, but I can only remember 1. Write your questions down and then get them answered. But late at night, you may have 5 questions. The next day, you only remember 1 of them. Write them down. The most ideal is when a student comes by and says, hey, Dr. C, I got these 5 questions. Boom, 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 boom. Okay, good. And it was very focused. Got what you needed. All right, very efficient. And these are the students that typically do great. Organization, very important, I think, if you want my recommendation. Making note cards of things like functional groups, okay? Information on the front, maybe a question, and then on the back, there's your answer, and you're like, okay, yeah. Oh, I forgot that. All right? Study guide. Just writing things out helps you learn. Okay? Anybody need any note cards? Index cards? I had a 3-ring binder. It's a little used, but it looks pretty darn good. Anybody need a 3-ring binder for handouts or somewhere? Anybody need a pocket periodic table? I usually give these for the high score on each test. Okay? I'll give one today. If you want another one, well, make high score on the test and I'll give you another. Okay? I love everybody to make high score. We'll give you all of them. What we got? Lab manual. Workbook lab manual. Okay? I usually just call it workbook. The second half is the lab manual. All right? All right. I created this. Questions for me. The lab portion. Pages are numbered with L's. By the way, there's a table of contents. Please know what's there. Okay. And the lab portion has a table of contents. And it includes an overview of lab, safety, requirements for lab notebooks, requirements for lab reports, checking into lab, instructions for checking into lab, which we're doing today and tomorrow. Also your check-in sheet. When we come to lab, I'll say, okay guys, check in. Well, the instructions, you've had them, okay? Or if you needed to, you've asked questions ahead of time, and we're good to go. Etc. Some information about a number of things here, instructions and descriptions, and then the labs. I may call this the lab handout because these used to be just handouts. Okay, so the lab handout for the solubility lab, which is our first lab, is on page 20L. And so here's your first lab. There's typically an introduction to the lab. about pre-lab. Pre-lab is your work to prepare for lab, including writing stuff into your notebook. Okay? There's the general information of lab notebook requirements, but then each lab handout has its own sort of more focused pre-lab information and requirements for that particular lab. I am big on being very, very clear, hopefully very clear and detailed in information, so you can read it and not have to say, what did he say? What did he say? I don't want you to have to do that. Everything is right there, so you can read it, read it, read it. Now, if it's not clear, let me know. I often will update it to make it more clear. Okay? What I don't particularly like is when you ask questions that are like answered multiple times here, and it's like you didn't even take the time to read, and now you're trying to ask questions. And like, why didn't you read it? Okay? But please ask questions that go beyond what's here. If you want an explanation, or you have interest in something else, or whatnot. And one of my syllabi, the subheading for the test for the course was organic chemistry, but the second title was how to follow directions. Okay, I'm big on following directions, reading things. Why? Because I think that will help you tremendously going forward. All right. So here we go. Blank slate. You know organic chemistry is chemistry of carbon compounds. What else do you know? Probably a little bit here and there. Mostly very little. What are you going to know come June 20th? Well, if you work hard and you're interested and you want to learn, you're going to learn and know so much more. I will ask you then, think back on May 20th and how little you knew. Okay? You can learn a lot, and it will do a lot for you. Biochemistry, pharmacology, courses going forward. Okay? Drug development. Who knows, you may end up working for NIH in drug development, cancer drug development. Who knows where you're going to end up. Okay. But organic chemistry will open doors for you. Okay, let's see about handouts. Do I have the handouts? I think we can get started, yeah? Again, number of things I could say. I want to get us started though. Any questions though at this point? All right, got to make each day count, right? Make it count. Y'all ready? Yeah? What time is left? 2:30? Okay. We'll see some of you upstairs today, 2:30. The rest of you tomorrow. Okay. Let's work hard. Let's be engaged, interested. If you ain't interested, I'm not sure where you're taking the class. Let's work hard. Let's be accountable for what needs to be done. Reading directions, following directions. Okay. Arriving 5 minutes before class starts, so you're not rushing in, etc. These things are mentioned somewhere, perhaps the syllabus. And let's also have a little fun and learn some interesting stuff, yeah? Review of atomic structure. There's our outline. That's what helps me know where we're going. Hopefully it helps you. Yellow page, DQ page. Something I've been trying to do. Basically, there's lots of questions out there. Okay, you could be working, but it's sort of random. Okay, these are questions where I would hope. Oh, everybody has looked at, so maybe we have some discussion in class, and you know that discussion of these questions might be coming, rather than some random number 23 in chapter. Oh, I didn't look at that. I know because we never said it. But these I'm giving you and said we may look at these. Okay? And of course they cover the content. This is essentially could be test 1, and you know half of test 1 right there. So that's what I call the DQ. The other handout we'll be looking at today is the functional groups and DUS warm-up. Physical properties will be a little later. And maybe that was it. Okay. Review of atomic structure. Here we go. Well, carbon. And hopefully this board will behave. Carbon. What's the atomic number of carbon? 6. Is it 6? 6. Then change. Let's write that here. Yeah. Let's look at the mass number, the different mass numbers, different isotopes. You know, what about carbon 12? Okay. That would be how many protons?
6.
6 protons. How many neutrons?
6.
6 neutrons. How many electrons? Assuming it's neutral, a neutral carbon atom. Is that 6? Neutral would balance the protons, 6 electrons. Is that right? 666, is that right? Okay. But we can have other carbons. We can have, what's the atomic number?
6.
This.
6.
Any carbon is 6, so usually that's not even shown, right? What about C13? What's the difference here?
It has an extra neutron.
Yes, extra neutron. Carbon 13. Percentages. Well, let's do carbon 14 here. Carbon 14. Difference?
It has
8 neutrons.
6.
Is that right? These add up to give you your mass number. Is that right? I haven't had Gen Chem in a long time. I have to rely on you guys. I know you guys just had Gen Chem recently, yeah? Gen Chem is a prereq to organic. Are there any other carbon isotopes? These are isotopes, right? They differ by number of neutrons. Okay. Any other isotopes? What was this here? This is where this carbon group, a methyl group, carbon 11. Is that possible? Yeah? What's the difference here?
5 neutrons.
Yeah, 5 neutrons. Everything else is the same, just different in the vary a neutron. These are natural here. These are natural isotopes. Natural abundance. This is like about 99%. This is about 1%. And then what about C14? We call that trace amount. I mean, it's a little bit. I rounded that off. Okay. C14 is radioactive, used for carbon dating the dinosaurs, right? Because the dinosaur took in carbon as it was living from eating. When it died, it no longer took in carbon, and the C14 had a starting point, and from there it's decayed. But it's still decaying today, and we can determine when the dinosaur died and thus when it lived. Natural abundance. C13 is only 1% approximately. C13 is very important for carbon NMR, which is covered in organic 2. Okay, when you do carbon NMR, you're only doing NMR on 1% of the sample, because C12 doesn't do carbon NMR. Carbon 11. Okay, this is man-made. You can make other artificial elements. This man-made element is a positron emitter. It's radioactive, just like carbon 14. And this is in the compound that I showed you. Okay, which is in one of the handouts. You can look it up on Wikipedia. I sent it in an email. It's a man-made, it's a positron emitter, okay, which is like an anti-electron. Okay? Where are these located at? Nucleus, what's in the nucleus? Protons and neutrons, is that right? And then the electrons are around the nucleus? Okay. Largely, reactivity in organic chemistry deals with the electrons. And we will not be doing any nuclear chemistry, never in this course that I teach. Okay? Typically, only electrons involved in reactivity. Okay. How many valence electrons does carbon have? By the way, on the back here, I mentioned carbon, some isotopes here. It's also isotopes of hydrogen. And I've recently added this to my handout here. Deuterium. It's an isotope of hydrogen. Hydrogen isotopes get their own names. Okay, these are just called carbon 11, carbon 12, carbon 13, etc. But H2 has its own name. It's called deuterium. It's just a hydrogen with an extra neutron, but we call it deuterium. Very common. It's actually becoming more common in drugs for certain reasons. A little information there. It's also H3. H3 is known as tritium. Tritium is radioactive. They used to deal with it out at the Savannah Riverside. So understanding isotopes. We'll see deuterium occasionally along the way. Okay? It's just a fancy H. All right? Now, did I just tell you enough to satisfy everything about that? I'm not sure, but you're going to read this. You're going to think questions. What do I need to know here? Okay? I'm introducing topics. And then from there, it's up to how much you want to pursue this information, et cetera, et cetera. Okay. Electron configuration of carbon. What is the electron configuration of carbon? We have what? What is this? 1s? And then what do we have? 2s? And then what?
2p.
S just has one orbital, right? One orbital. And then 2p? And this is what? 3? And we know what those look like. We know their directionality towards each other, orthogonal, etc. We fill these in. Remember things like Hund's rule, off-ball principle, Pauli exclusion principle. Basically, we got how many electrons? 1, 2, 3, 4, 5, 6. Is that right?
Yes.
Ground state configuration of carbon. I don't know what that's useful for. What is that useful for? Because anytime we're going to hybridize. We're going to get a hybridized ground state. This is sort of, what was the purpose of this? Y'all can do ground state configurations? What's the purpose of doing it, though? I don't. Can anybody tell me the purpose of doing it? Aha! Don't do anything unless you know the purpose of doing it. Okay, guys? Why did you do ground state configuration? Yes.
Is it to see how many electrons are available towards bond?
Okay. I mean, we could talk about things, but that's the type of thing I want you to get at is, let's not just do stuff so we can do it and have tests and what's the purpose of doing this stuff? Think like that, okay? Get outside of the material and say, what are we doing here? Why is this important? Question.
I was going to say, does it have to do with understanding the orbitals?
Yeah, there's orbitals. What does an S look like? I mean, there's lots of questions that can come from this. My big question was just this thinking question. Why? What are we doing here? What does an S orbital look like? Like a volleyball, okay? All right, the nucleus sort of here, and the electron is all around it, okay? What is an orbital? Okay, that's an S, yeah. What's a P look like? Uh-huh. Dumbbell shape, nucleus here. At the nucleus, there's really a node. There's no electron density right there. The electron densities, okay? And you know what an orbital is, right? Where's the electron at? There. All right? The book on that right there is about this thick. All right? You got to think, okay, what really is this? How much do I need to know to be able to be literate here? How many valence electrons does carbon have? Valence electrons, what is that?
4.
Outer shell, valence shell. But typically we'll only be dealing with the valence electrons. And this is, we ignore that down there. We're not going to hybridize it. And very often I'll talk as if that's not even there. We're going to be focused on valence electrons. Types of orbitals. Got there? Roman numeral 1, did we cover everything? I consider that to be review, right? All right? Trying to give you some organic lingo, though. Things that we're going to talk about it. But we will be hybridizing. We'll be hybridizing, because this looks like a lone pair. It looks like 2 electrons, a lone pair. Carbon typically does not have a lone pair. Okay, bonding. Covalent bond. Everybody know what a covalent bond is? Two electrons being shared between nuclei. Yeah. Orbital overlap. Okay. We can look at hydrogen. Hydrogen has how many valence electrons? 1. Okay. Is hydrogen with 1 electron happy? We get to what? Noble gas configuration. As some sort of basic guidelines for bonding. Somehow it makes the hydrogen happy to become more like helium. Okay? For various reasons. Why?
It's more stable. It's more stable.
Yeah, I would say that's really the question, what I said. Why is it more stable? Okay. There's lots there. But achieving noble gas. How many electrons does hydrogen need to achieve noble gas configuration? This needs 1, you're right. And then we have a total of 2. So if you had 2 H atoms, these guys could team up. And this could get to something like this. And now we have electron density in here. And this becomes a magical thing of the two electron covalent bond. And that book is this thick, or this thick. Okay, the magic of these 2 electrons interacting to make a bond. All right? We're not going to go deep. We're just kind of skimming the surface here to get to a certain point. Again, all right, so much there. If we can come back here, this is really, what type of orbital is this electron in? Just 1 up.
Yes.
If you did a ground state, you just have 1s, right? Okay. I could do the whole thing. Okay, that's there. The other one's the same thing. Basically, that is really overlap of 2 orbitals, right? What is this? 1s interacting with 1s. These orbitals interacting, and it really makes a new orbital. Again, that thick book. It makes the bond, but importantly is what orbitals are overlapping to make the bond. And in this case, it's 1s and 1s. All right? There's no hybridization. When we get to carbon, we're going to have hybridization. Now with carbon, how many electrons does it need to make noble gas, neon? It's got 4 valence, it needs 4 more. And it turns out each time you make a bond, you get 1 more electron. And by the way, the H, 2 electrons, now when we do a sort of octet count, you get to count shared electrons for each H. So when you look at that structure, you say, I still got it up here, how many electrons are around this H? Well, those 2 get to count for that H, and it's got 2. How many's in this H? Well, those 2 get to count for that H. They both have 2. Sounds like there's 4 electrons up there, but they ain't. It's just, they both get to count it this way. They both have 2, they both have a duet. They both have the helium noble gas configuration. This is the language. Okay. With carbon, because carbon needs 4 electrons, how many bonds is carbon going to make?
I don't know if we can do this.
Y'all been in this classroom before? Does this board erase any better than I?
It's true.
That word is horrible, it never erases.
Got some sticky stuff. Carbon. Okay, let's do this systematically. I'm going to go across, leave some room on the paper. Okay, because we're going to do carbon first. How many valence electrons? 4. We're going to put 1. Remember how I put H? I put 1 dot, 1 electron. Carbon has 4. Let's put 4 around it. Okay? How many bonds does it need to make? Okay? If we bring in, remember the H with 1 electron? All right? Instead of a dot, let's call that an X. So I keep it separate from these dots. All right? We can bring in an H, and it's 1 electron, and team up with a carbon electron, we just made a CH bond. But we can do that how many times? I'm bringing in the H and it's 1 electron, the H and it's 1 electron, the H and it's 1 electron. And now every H has a duet, that H has 2. We can show this in a more classical dashed, which indicates 2 electron covalent bond. We just got to this point. This H has, each H has a duet, as we get to count. The bonding pair is 2 in each H. Okay? By the way, H always makes just 1 bond. H is always going to be on the periphery, because it doesn't make 2 bonds. Carbon, though, how many electrons does it have if you do a octet count? 2, 4, 6, 8. Those bonding electrons you get to count all for carbon. This is sort of just a bookkeeping approach when we do that. But this is common bonding for carbon. Common bonding, which we're going to do, is for carbon, 4 bonds, 0 lone pairs, LPs. We're going to see an LP in the next example. Let's move to nitrogen. How many valence electrons?
5.
5. 1, 2, 3, 4, 5. Let's pair up there. How many bonds do we need to make? 3. We're bringing an H here. And by the way, I'm just bringing in H. I could bring in a variety of H's. It doesn't have to be an H. I can bring in another H. I can bring in another H. We get to that. And that would be more classically shown as that there. H is good, 1 bond, duet. How about nitrogen? How many electrons are around in terms of octet count? 2, 4, 6, 8. Nitrogen has an octet. This is standard bonding for nitrogen is what? 3 bonds and 1 lone pair. I'll try not to write so low. Standard bonding, that's what we're looking at. By the way, what's the name of these compounds? This is the compound. Methane, 1 carbon. Nomenclature, covered by video only. It was in a handout I emailed you in the pre-course meet and greet, the original email. Okay, anybody been watching Nomenclature yet? Yeah? Okay, pretty straightforward? Methane, ethane, propane. Okay, 1 carbon, alkane, methane. What's this? NH3. Okay, ammonia. Of course, these can be written. Right on the board, so then I'll have to erase it. CH4, NH3. We know NH3 has a lone pair though, because we know structure and bonding. Okay. What's next? I'm coming across oxygen. How many valence electrons? 6 valence electrons. If we bond H's, how many bonds are we going to make? Bring in 1 H and it's 1 electron. Bring in another H. Here we go. What do we got? There, but we know there's 2 lone pairs there. And what do we have here? Around the oxygen, 2, 4, 6, 8, octet. And what do we have? Water. Right? Standard bonding for oxygen is what? 2 bonds and 2 lone pairs. Standard bonding for oxygen. By the way, why am I coming around only 4 times and then pairing up? 1, 2, 3, 4, 5, 6. Why don't you 4 around and then start pairing up?
You have to complete the first 4 little.
Because what I'm really doing is I'm filling these 4 valence orbitals. There's 4 valence orbitals, right? That's really what I'm doing here. I got 4 places to put electrons. All right? And the 4 orbitals are being used here. Now they're being hybridized. We'll get to that. F. 1, 2, 3, 4, 5, 6, 7. How many bonds do we need? 1. We can bring in an H, single electron. We have just HF. Hydrogen fluoride. We know when we have HF, then halogen, 3 lone pairs there, right? Okay. We're doing Lewis structures. We're doing a complete structure with lone pairs. Bonds is dashes here. You always need to show lone pairs. Now, very often you will see non-lone pairs not shown. Either because of just convenience, you don't want to use ink, maybe a drawing program, it's a little bit cumbersome to put in the lone pairs. You need to know when they're there though. And then when asked to give an official, formal Lewis structure, you definitely need to put them there. HF. This is the same thing for all the halogens. By the way, what's common bonding for sulfur? Same as oxygen. What's common bonding for fluorine? 1 bond, 3 lone pairs. What's common bonding for bromine? Okay, same group trend. All right, common bonding for iodine, same as fluorine. The difference is, once you drop down here to the 3rd row, you can expand its octet because these now have d orbitals. See, these guys are all like carbon. They're the 2s and 2p. But when you go to the 3 shell, you have the d orbitals, and that allows for more complex bonding, expanded octet. So sulfur, you can have other types of common bonding, but sulfur also does this. So these guys tend to be sort of dual. They behave just like oxygen or just like fluorine, but they can also do other things as well. Okay, common bonding. Now, if you see a carbon and it doesn't have 4 bonds long pairs, that means it's not common. And if it's not like this, it's probably going to have a charge. Okay? This is common bonding for neutral atoms here. We will occasionally see non-common bonding. And there's exceptions to everything. Stephen said that if it ain't common bonding, it probably have a charge. Well, probably. I didn't say that. There's always an exception. Somebody want to be the official eraser? This over here is a little better. Okay, common bonding. Common bonding. Let's see, A, definition, octet rule, Lewis structures. We're in consideration. I think it's all there, okay? We're just sort of setting the stage. As we move forward, we'll build upon these things. I think we're down to B. Let's try to put some structures together from formula. CH4O. CH4O. See right there? It's good? Put together a structure for that, just like we did here. Basically, I put together a structure for CH4 here. How did we do that? What is the strategy we need to do? Is there a systematic approach? Okay, I would recommend bonding the heavy atoms together first. Heavy atoms mean not hydrogen. We have one C and one O. Is that right? I would recommend bonding them together. Hydrogen only makes one bond. It's going to be on the periphery, right? Very important before we get going, though. How many valence electrons are we dealing with? Because when we get done, we need to show all valence electrons, right? Well, it'd be good to know how many we need to show. How many in CH4O? Carbon has 4. 4 H's, that's another 4. That's 8, and then 6, 14? Okay. 14 valence electrons here. Bond to heavy atoms. Now we can decorate this with hydrogens. I'd recommend putting H's on carbon first. Just take that as a recommendation. Fill the valence of carbon. How many H's on carbon here? 3, because carbon makes how many bonds? There you go. Carbon now has an octet. Do we have another H?
Yes.
You want to just slip it here?
Yeah.
Carbon don't make 5 bonds, not on this planet. Where do you want to put it? Okay, what's common bonding for oxygen?
2 bonds. 2 bonds. 2 bonds.
Okay, 2 bonds.
2 bonds.
How many valence electrons up here? 2, 4, 6, 8, 10. Well, we need to have 14. That means we need 4 more electrons. In terms of pairs, that would be 2 pairs. Where do you want to put the 2 lone pairs?
Oxygen.
On oxygen, because you do know that common bonding for oxygen is 2 bonds, 2 lone pairs. Common bonding for carbon, 4 bonds, no lone pairs. See how everything just kind of fell together there? Yeah? How about the next one? C2H6O. Can you do a structure there real quick? Somebody got it? What you got? I erased my compound. Anybody know the name of my compound we had up there first? What was it? Functional group. What functional group do we have up there in that compound I erased? It's alcohol, yeah. One carbon alcohol, methanol. Not methane, but OL ending. Methanol. Let's see here. I saw the same here. I wonder if anybody has a different one because there's two constitutional isomers. Heavy atoms first. What about carbon? Carbon O. H is on. Fill the valence of carbon. How many H's here? How many total H's do we have? 6. 3, 4, 5. Good, good. 6. Both carbons have an octet. 4 bonds. How many valence electrons? It's probably 4 short of what we need. If I put 2 there and 2 there, how many valence electrons are in this one? You did that first? Was it 20?
Yeah.
4, 4 is in 6, we 14, and that's 20. That's 20. I don't have to look at it. You better be 20. Should be. Is it 20? Okay, there you go. That's 2 carbon alcohol. Ethanol. Yep. Did anybody get something different?
Oxygen in the middle.
Oxygen in the middle, yes. We could have gone COC. Fill the valence of carbon with H's. Carbon is good. How many H's we got? 6? That's 16 valence electrons. 18, 20. 20 valence electrons. That's a different compound. Different connectivity. Bonds are connected differently. First compound, carbon is bonded to carbon. And the other compound, carbon is not bonded to carbon. That's an alcohol. That over there is a, probably don't know it, ether. Functional group. You've got a list of them. We'll get to them. Functional groups are just particular arrangements of atoms. Okay? A carbon OH is alcohol. What is an ether? It's an oxygen bonded to 2 plain carbons. Mostly plain. Is this oxygen bonded to 2 carbons? It ain't an ether. Okay? We should get to functional groups today. If not, you need to be looking at them. These have the same formula, but they're different compounds. What are they? Constitutional isomers. Okay? They're going to have different properties. In fact, they are. This is a liquid at room temperature, and that compound is a gas at room temperature. Because this compound has lots of hydrogen bonding IMFs. You know what an IMF is? That was on Star Wars, right? The IMF. And that over there doesn't have hydrogen bonding. So physical properties, which you have a handout on, and there's a section on hydrogen bonding. Okay? More hydrogen bonding, greater IMFs, higher boiling point compared to the gas. Okay? Constitutional isomers, same formula, different connectivity. Elements are connected differently. These are also saturated. These have the maximum number of H's. C and O, C2O. And what was the rest of the formula? 6. The maximum H's that C2 and O can have is 6. Okay? It's said to be saturated. We'll talk more about these. Both of these are saturated with maximum H's. In the future, we'll do something like C2H4O. And if you know 6 is the max, then 4 is less than max. And if you have less than max of H's, it's called unsaturated. All right, there's a handout on that. You have it already. Okay, what's the next? Let's try double bond. Uh-oh, I just gave it away. CH2O. Well, maximum for CO is 4. CH4O, that was actually maximum. This is less than that, CH2O. You do a structure for this. How many valence electrons? Carbon 4, 6, what is it, 12? Okay, I may not give headings and whatnot on the board, especially if I can't erase. But where are we at? We're under 2C, right? Roman numeral 2C. If you need to, you can always make a quick 2C. Whatever, to help. What do you want to, how do you want us to do this? How many valence electrons again?
12.
Yeah, 12 valence electrons for the one we're doing here. You want to bond the carbon and oxygen first? Then let's fill the valence of carbon. What we got? C2? I mean CH2? I need another H here, it seems like. Okay, systematic. What do we want to do next? I'd rather not just say, hey guys, it's going to be a double bond. I want us to go through a process of just seeing how that knowledge comes. What I would do here first is, we want to start putting up lone pairs. We got 2, 4, 6. We need to put 6 more electrons up. And if you had to fill a valence, which one should we make sure is filled, carbon or oxygen? Which one is more demanding of a filled valence? Oxygen. Oxygen is more electronegative. Oxygen demands electrons more. It's greedier. Let's satisfy the oxygen. How many lone pairs do we want to put around it to satisfy it? Does that oxygen now have an octet of electrons around it?
Mm-hmm.
2, 4, 6, 8, yes. The oxygen is now satisfied. Are we done? That's 12 valence electrons.
Carbon is not filled oxide.
What else do we need to do? Not put up 12 valence electrons.
Octet.
Oxygen's got an octet. What about carbon?
It doesn't.
We want to try to get carbon an octet. By the way, this structure here has charge. I don't know it has charge. Because remember, is that typical for oxygen?
No.
Then I said it probably won't have charge. Is that typical for carbon?
No.
Probably going to have charge. What's the charge of the oxygen here? How do you do formal charge? How many does it own? An atom owns its lone pairs, 2, 4, 6. And it owns one of each bond. It owns 7. And this is not an octet count. An octet count, we count that as 2 because the bond just counted as both. But in terms of what it owns, it goes back to sort of, you remember how we had the dot and the X? The nitrogen brought the dot and the H brought the X. When we do charge, we just look at what it kind of brought to the dance. We don't count the X in that. It owns those in one of these. There's a formula somewhere, but that's how I do it. It owns 7. How many is oxygen supposed to own, or typically own, from the periodic table? 6. So it's got one more than it should have. And if you got an extra electron, what's your charge? Negative. How many does carbon own? One of each bond, so it owns 3. But it's supposed to be owning how many? 4. So it's missing an electron. And if you're missing an electron, the charge is going to be positive. You need to show formal charge, and I would recommend circling formal charge. Most people do. So if we showed that structure, it's now a complete Lewis structure. But is it the best that we could do? No, there's two reasons it's not the best. First off, carbon doesn't have an octet. And the other thing is you'd rather not have charge if you can not. Now, it's net neutral. Right, you see it's net neutral? We knew that from just looking at the formula, because if the thing was charged, it should have shown it with the formula. But it's net neutral. We see it's net neutral. How can we get a better structure? We're going to have to ask this oxygen to share. Hey, oxygen, this carbon needs some bonding. So these electrons, and we're doing our first mechanism, let's take these electrons and move them in here. It's like this. We're going to make them just come in here, fall in here like this. We're not moving the lone pair over here. It's more just moving this in like this. And we'll do this plenty. This is the very first time. And what does that electron movement give? What does that arrow mean? Well, I told you what it means. We move the electrons in. And so now we have not one bond, but now two. And over here there's H and there's H. How many lone pairs left on the oxygen? Two. That remaining. This one fell in to make the other bond. Two remaining. Does everybody see what we just did? What does the arrow mean?
Share.
We had to ask the oxygen to share. Now look at it. Now does the carbon have an octet? Now you get to count this bonding pair as for the octet count 2, 4, 6, 8. What's standard bonding for carbon? 4 bonds. 1, 2, 3, 4. It's a double bond, but that's 4 bonds, no lone pairs. That still is true. Oxygen doesn't have an octet. 2, 4, 6, 8. Even though it's shared, it still has an octet. And what's standard bonding for oxygen? 2 bonds, 2 lone pairs. So now we have standard bonding, everything has an octet. We no longer have separation of charge, which is a higher energy state if you take physics. It's much better structure here. Okay? And if you were asked to draw a structure here, this would be probably the better one. But that over there has some reasonable. I used a resonance arrow, because these are actually resonance structures. We will talk a lot about resonance structures. We'll eventually cover it during test 3 material. What's the definition of resonance? I think it's right there on I, right? Okay? Please be thinking about, a lot of textbooks cover resonance in chapter 1 or 2. I think it's a little early. We kind of ease into it a little bit. Okay? All we did is move pi electrons. We haven't called these pi electrons yet, but we will later. We didn't move any atoms. Okay? Start reading about resonance and getting a working definition on that. Yeah? You halfway there? Good. Okay. Degrees of unsaturation. Formal charge, we did that. Okay. Let's try D, HCN. By the way, this is 1 VUS. We saw that from formula. Because we knew 4 was max when we only had 2 H's. We'll do more of that. Things like this are for your notes, so then we talk about it later. You can valence electrons in HCN. 10?
10.
I think it's 10 valence electrons. Cn, with the H on carbon. We have no more atoms. Lone pair on nitrogen. How about we do that? 2, 4, 6, 8, 10. Done? Well, if this is our structure, we at least need to show charge. Charge of nitrogen. How many does it own here? Owns how many?
7.
Owns 7. How many is nitrogen supposed to have? 5. It's got 2 more than charge. -2. Charge of carbon. +2. Because it only owns 2. It's supposed to have 4. Is that the best we can do? What do you want to ask the nitrogen to do? How about if we take these electrons and move them in here? That is a resonance structure. We have HC. Now we have double bond, 2 lone pairs here. Is this good? Are we done?
No.
This is minus, this is plus. Is that the best structure, or can we do better? What if we do it again? Ask nitrogen to share again, and we get to what? Triple bond. Is that possible? Yes. How many lone pairs left on nitrogen? 1. How'd you know this? Because it was a progression of thought using our mechanism arrow. I mean, it's all nothing magical about it. If there's 2 there, then that falls in, there's only 1 left. Are we done now? Carbon have an octet? 2, 4, 6, 8. Does nitrogen have an octet? Standard bonding for nitrogen? 3 bonds, 1 lone pair. The triple bond. It's 3 bonds. Okay. Hydrogen cyanide. It has 2 DUS. Maybe we can look at DUS now. Many of my handouts have what I call warm-up problems. Dr. Hager, I got this terminology from him. He uses it a little bit differently. Questions that sort of show you where we're going. May not be able to answer them now. Hopefully when we're done, though, before test day. Okay. You can also use these like DQ. DQ, everybody knows that these are ones that we could maybe talk about. Basically, it's just extra I give you tons and tons of problems. Okay? Work until you're satisfied that you're good to go. All right? Some of my kind of homework problems sometimes tend to be sort of thought-provoking or maybe striving for high interest. So some application. Okay? It's basically showing you types of questions that I'll be asking you. Functional groups there. I reckon let's look at DUS first. Then we'll look at functional groups. Everybody good? The lighting is okay? Got your solvers? 1 and 2. Flexing each arm, and then double. Good to go? DUS, very important. can help you along the way. Two ways to determine DUS, from structure and others from formula. One double bond is one DUS. One triple bond, that's a T, is T2 DUS. Basically, each pi bond is a DUS. Once we clarify what a pi bond is, okay, if you don't know that yet. Also, one ring is a DUS. A DUS is where you essentially remove two H's from max. Every time you reduce two H's from max, which is called saturated, every time you reduce two, that's one DUS. So one DUS removes two H's. For example, ACN, which we just did, I told you had two DUS. That's because if you just had CN, it turns out that maximum H's for C and N is 5. And we'll show how you know this later. 5 is saturated. That's less than 5. How many less than 5 is there? It only has one. What's the difference between 5 and 1? 4. That's called subtraction. You learned that in 4th grade? Okay? That's the difference. Yeah, missing 4. But every 2 you're missing is 1 DUS. So if you're missing 4, how many DUS is that? That's some good math. All right? That's 2 DUS in terms of that. Now saturated would be something like this. And you could do a structure. By the way, structures are sometimes, or formulas, the precise formula of this is CH5N. Right? Sometimes formulas are shown with a little bit of structure there. Because it's like the CH3 and then the NH2. So you'll see this a lot, where this is sort of the official generic formula. All right? So, but that's totally saturated, and there's no double bonds there, or triple bonds. There's also no rings. Because if you have any of those, it would be DUS. This is saturated. This compound has one double bond, so it's one DUS. Okay? That implies that it's missing 2 H's from max. Well, this is 2 carbons with maximum H's. And so this is 4, but this is 6. Okay? So it's missing 2 compared to this. It's 1 DUS. There's sort of multiple ways to see this. Missing H's, presence of double bond. How about a ring? This is a 3-membered ring, carbon ring. But this is a 3-carbon non-ring. Well, the fact that there's a ring here means it has 1 DUS. We said that right there. But since it has 1 DUS, that also tells us it's missing 2 H's from max. 3 carbons, maximum H's is 8. And you see over here, that's only 6. The difference is over here, the 2 carbons are bonded to each other, and if you're going to do that, you have to get rid of 2 H's. Okay? So there's no double bond there, but there is a ring. A ring requires eliminating 2 of the H's. How many ibuprofen here? Got a hole punched there. DUS. There's none out here. That's it.
5.
DUS?
5.
I see 1 ring. And how many double bonds? 4. That's my, okay, that's a benzene ring. There's 3. 4 double bonds and a ring, 5 DUS. Okay, you can see it from structure. That's what we're doing, Roman number 1, from structure. Okay, that's probably enough to get us going on that. How about from formula? Hydrocarbons. This is a compound that just contains hydrogen and carbon. Pretty sophisticated name, right? CH only. We're gonna say a lot of the stuff we said up there, but more focusing on formula. The maximum number of H's, which is called saturated, can be calculated by a formula 2n plus 2, where n is number of carbons. Let's do that for up here. 3 carbons. What's maximum number of H's? How do we get 8? Well, you can get that by saying, okay, 3 carbons, n is number of carbons, 2 times 3 is 6. 6 plus 2 is 8. That's how I knew it was 8. Okay, so 2n plus 2 formula. Where does this formula come from? The formula knows the common bonding of carbon is 4 bonds. And it knows if you start bonding carbons together, it's no way to count. It knows it's a smart formula. C5, what would be saturated? 12. So C5H12 would be saturated. Can C5H12, can that compound have a ring? It cannot. Because that means it would have to have a DUS, but formula tells us there's no DUS. So think about how powerful that is. Can this compound have a double bond? No, it cannot. If you were to try to draw that compound and put a double bond in, you would have the wrong formula on the board. Something would be wrong. So this allows you to see a lot from just formula. What about C5H10? Real quick, how many DUS is there? 1. I know it's 1. Because max is 12 and it's missing 2, and every time you're missing 2, that's 1 DUS. Okay? How many rings can this compound have?
Wait.
Or a compound with this formula, how many rings can it have? It can have 1, or it could be 0. Can this have 2 rings? No. How many double bonds can this have? 1 or 0 if that DUS is a ring. Okay, but what about when heteroatoms are present? Heteroatom is a non-carbon. If I say heavy atom, that means everything except H. Heteroatoms, non-carbons. Basically, how do you adjust your formula? Okay, because the formula doesn't say anything about nitrogens or oxygens. Well, here's what you have to know. A halogen counts as an H when you're doing the formula. A nitrogen subtracts an H, and an oxygen, good news is you just ignore it. Because an oxygen, it doesn't change anything. Because an oxygen, you can just slip in. Don't write this on your paper. But see, I can just slip in an oxygen here between the C and the O. And it hasn't changed anything. But I can't just slip in a halogen. I'd have to get rid of an H. Don't write this, it would be confusing for you. I'd get rid of it. But if I see a chlorine, I can think, well, it just replaced an H. Okay? You got to be careful and not get this backwards. I see students get this backwards, particularly with nitrogen, subtracts an H. And this is the type of thing where I can't explain it to you. You got to make this mistake, and then I can explain it. Right? Because it'd take me an hour to explain it. But if you do it and ask, then it'll be like, okay, be careful there. For example, Prozac. How many DUS in Prozac? Well, the answer is 0. How do we get to it? We basically want to get back to CH, because if we have just CH, we can use our 2n plus 2. What does F count as?
Plus H.
So we get rid of the F's and change this to 21. Can we do that? What do we do with nitrogen?
-4.
So we get rid of the nitrogen and change this to,
20.
change that to 20. And what do we do with O?
Ignore.
Just ignore it. So this essentially becomes 1720. Now we can do 2n plus 2. 17, 2n plus 2 would be
34.
36. 17 times 2 is 34, plus 2, 36. Okay? 36 is saturated. How many are we missing?
6.
Missing 16. So what's the DUS? 8, because every 2 you're missing is 1 DUS. Prozac has 8 DUS. We can look at structures in the syllabus. Lower left, do you see the 8 DUS? 8 DUS? You better see it. I mean, the formula told us it should have 8. Do we see 8? 6 double bonds and 2 rings. Now the formula of Prozac, there could be 1,000 different compounds. Only one of them is Prozac. But every one of those 1,000 should have 8 DUS in the structure. Okay? And so there's plenty of practice. How many DUS in the process? I hear an 8. Anybody else? The proxim, top left? That's also 8, right? 6 pi bonds and 2 rings. Pi bond is the second bond over a double bond. Did we cover everything there? DUS? Very useful, very useful. Question?
Okay, why did you say that ibuprofen is 5 if it should be 4, if it only 1 and then the magnesium is 1?
We said ibuprofen was...
It's 5, isn't it 4?
Ibuprofen is going to have a carbonyl, CO double bond, right?
Yeah, but then why is then oxygen and oxygen?
Could we have 4 double bonds and 1 ring? We see inside the ring 4 double.
Which one you talking about?
Okay, so for the carbonyl in ibuprofen, we count the double bond, right?
Where's ibuprofen at? I don't think ibuprofen's on this page.
No, it was on the
It's on the DUS page?
It's one of these right
Ibuprofen at 5?
now. Yes.
4 double bonds in a ring at 5?
Yeah. Okay, then how do we count the carbonyl in the naproxen as well?
Certainly, you would always count. Carbonyl's a double bond. Keep looking at it. Okay, functional groups. Okay, first hydrocarbons. Alkanes. Alkanes are saturated hydrocarbons. That's pretty much almost meaningless. R group. There's no R on the periodic table. R is a generic, typically meaning just a carbon group. Okay. That's very general, almost by using these trying to show here. It'll make more sense come. Okay, so saturated hydrocarbons. Alkanes, there's also alkane nomenclature, which probably says the same thing. Also, seeing the next ones help us understand what that one was. The next is alkene. Alkene has a carbon-carbon double bond. So we call that an alkene, as opposed to saying carbon-carbon double bond. If you have a carbon-carbon triple bond, that's called an alkyne. Functional groups must be spelled correctly. Okay. Next one on this list of hydrocarbons is aromatic compound. Benzene is the most common. Benzene ring. What is an aromatic compound? Gauche over here. What's an aromatic compound? All atoms in the ring have p orbital. Okay, that's the definition of aromatic. Everybody know what a p orbital is? How to recognize it? Bonding? We haven't done that quite yet. That's coming, so you'll be able to better understand this later, but it's very important to understand what an aromatic compound is. All atoms in the ring have a p orbital. And that's just a starting point. There's other things that go along with that. Okay. Okay, compounds containing a CZ. Z is not often used too much. Z typically, I reckon, means sort of electronegative. Basically, hetero atoms. Things other than carbon or hydrogen. Alkyl halides. This is going to be a carbon group bonded to a halogen. For example, methyl bromide or methyl bromomethane, or we'll learn nomenclature. I've got to be careful here, guys. It looks like the bromine is binding to an H, yeah or no?
No.
We know that the H's are really on the periphery of the carbon, and the bromine is bonded to the carbon. But you'll often see structures drawn like that. I typically tend to prefer sort of drawing it like that, showing the CVR bond. Particularly when we get to reactions where we need to see that carbon-bromine bond. All right? That's one thing about sort of structures is you'll see them drawn a variety of ways that sort of lead to possible confusion, especially when you look at them for the first time. That's just one of the things about organic chemistry. But by working more problems, and by the way, a lot of my problems I intentionally show you compounds different ways. What I don't want you to do is I show you the same thing all semester and you go take another course like, I never saw anything like that. So I give you more of the flavor. But I point these things out. Add one in here. Aryl halide. This is an aromatic ring bonded to a halide. Benzene bonded to that would be an aryl halide. Particularly aryl chloride there. Alcohol, carbon group OH. Remember we did methanol earlier? Okay. Ether. Remember we had two constitutional isomers? And ether is where you have an oxygen bonded to two different carbon groups. Where the alcohol, the oxygen was just bonded to one carbon group. Ether. Amines, nitrogen. Now up here, when oxygen binds to one or two, it had different names. With amines, the name stays the same.
The nitrogen can be bonded to one carbon group, or it can be bonded to two, and that's sort of condensed, but that nitrogen is making bond to two different R groups or carbon groups. This nitrogen, I can draw it out. Basically, it's bonded to three different R groups, and of course, lone pair. That's standard bonding for nitrogen. Instead of changing name when you add R groups like we did here, we just say primary, secondary, tertiary. If nitrogen has one R group, it's primary. If it has two R groups, it's secondary, and on down the line. So it's still an amine, though. So tertiary amine. We need to know what that means, and we'll be using tertiary amines or primary amines. Of course, nitrogen makes two bonds with one pair. And this we would call that sort of condensed. We don't have to draw out the two H bonds. You just have to sort of know they're there. And if you're asked to draw a full structure, you'd be able to do that. Thiol. Thiol is analogous to an alcohol, but it's sulfur, and sulfur is under oxygen in the periodic table, so it's the same exact bonding. Sometimes this is called a mercaptan, or a mercapto group. Hydroxyl group, thiol or mercapto group, mercaptan. It would be an amino group. Okay. Analogous to an ether is the sulfide. Sulfur bonded to two R groups. Can also be called a thioether. That's a pretty common name. Thio being sort of meaning sulfur. And sulfur compounds are not hugely common. Just see them a good bit in biochemistry. Sulfides and even disulfides. Questions on that page? Pretty straightforward. What are we looking at? Common bonding arrangements of atoms. We get certain names, so now we can refer to them. For example, at some point we may look at the chemistry of ethers. Okay. Yeah, these are particularly good for note cards. Structure on one side, name on the other, and any other miscellaneous information. Help you learn these. Y'all seen functional groups before? Where have you seen functional groups?
I did cellular and molecular biology.
Okay. Organic is not a prereq for cell? Should it be? You were able to handle organic there?
Yeah,
Okay. Did you learn, had to learn functional groups, or?
like not very well. I just got some basic like ether.
Okay, next page is, next table is functional groups that contain carbonyl group. CO carbonyl, C double bond O. Many functional groups contain carbonyl. Carbonyl is not a functional group. It's a component of many functional groups. Aldehyde, carbonyl, R group on one side, H on the other. Aldehyde. R group on both sides, ketone. Now, of course, the oxygen is not going to make any other bonds because it already has its two bonds, two lone pairs. The carbon here, there, ketone. R group on one side, OH on the other, carboxylic acid. And that is the only functional group that's called an acid. It's sort of almost the only acidic organic functional group, although there's kind of a couple others. But the others just have like an R group, and that's the only reason it makes them organic. The business end is not organic. Carboxylic acid. Ester. Like a carboxylic acid, except the OH is OR. So there's R on the carbonyl and also R group, the carbon group on the oxygen. Ester. Amide. Carbon group on one side and nitrogen group on the other. And again, with the nitrogen, if we start putting R groups, it remains an amide. Where up here, we put an R group, it became something else. The nitrogen can have, basically, if it's bonded to just one carbon here, that's a primary amide. So how many NH bonds in a primary amide? How many NH bonds in a primary amide? Two. How many NH bonds in a tertiary amide? Okay, so questions like that could easily be asked, right? Because if there's only one carbon, the other two things are implied to be H's, right? Acid chloride, or sometimes called an acyl. Acyl. A carbonyl group is often called an acyl group. That right there is an acyl. A carbonyl with a carbon group, R group. And so that's an acyl chloride. Called acid chlorides because they're often made from a carboxylic acid, replacing the OH group with a chlorine. There's a couple others I want you to know because I think they're pretty darn common. They're not on this. This list, by the way, did not come from the Klein textbook. I think it may come from Smith. It's probably written on the first side. This page is, these are the functional groups I want you to know. A couple others are the nitrile group, C triple bond N, R group here, like that. We call it a nitrile. The group itself is called a cyano group. We mentioned this on Friday, didn't we? Not cyanide, but cyano. Sulfonamide. This is a SO2. That sulfur has an expanded octet, 2, 4, 6, 8, 10, 12 electrons around it. How many lone pairs on this sulfur? Because I'm not always showing lone pairs, right? Like how many lone pairs on that nitrogen? Those are the types of things you need to know. How many lone pairs on the sulfur?
Typically 2, but none right now on that structure.
Typically 2, if you consider it being like oxygen. Oxygen is usually, but this is more of a unique, expanded octet version. So how many here? How many lone pairs here? You said it. None. How do you know there's 0? How do we know there's 0 lone pairs here? What's the charge of this sulfur?
It doesn't have a charge.
It better be neutral, because if there's a charge, I should be showing it. And it's my fault. You assume it's neutral. Well, is it neutral? How many does it own?
6.
It owns 1 of each bond. How many does it own?
6.
Owns 6. How many is it supposed to own?
6.
6. Neutral. If there was a lone pair there, the charge would be 2 minus. Because it would own 8. But if it was 2 minus, I should have showed a charge. You assume it's neutral, and you see 6, it's only 6, so there's no lone pair, right? But up here, there's a lone pair. There's a full structure here. This would be, we would call this more condensed. You can do that sometimes. Okay. Very common. You just have to know what's there. Amide, amide. See, this is where the nitrogen is binding to a sulfone. So it's a sulfonamide, or a sulfonamide, it's pronounced. That's just a regular amide. By the way, this does have a long name. This is where the nitrogen is binding to a carbonyl. The long name of that up there is carboxamide. But usually for carboxamides, it's just shortened to amide or amide. But you would never shorten this, because if you just call that an amide, you're referring to that one. This one we say sulfonamide. Occasionally you might hear sulfonamide. That's kind of. All right, tomato. What functional groups do we see down here? Good looking molecule here. See this amide? Primary amide?
Yes.
What we got here? Ether. See, these are our old name for you, but look good? No? And in my workbook, I have a page of drugs, and there's all types of questions there. One of them is identify all functional groups. How many DUS? It's a pretty comprehensive page of questions related to drug structure in the workbook. So you got to find problems to work, and you know the topics. What topics have we covered today? DUS. Functional bonding, functional groups, charges, okay? And you work problems around these topics. And you write down your questions. Remember? Don't forget all your questions. You write them down, get them answered. Particularly before test day. It's never good when you take the test, you're like, ooh, I should have asked about that. A little too late for me. At least the test. Even if you don't do it on the test, maybe after the test you're asked to do it.
Are those two compounds in a specific class of functional groups, you know?
Or two, which,
Nitro and sulfonamide?
there are 2 additional ones I want you to know.
Two down there.
No, I'm saying like, are they,
These 2 here?
are they in a specific class we need to know of functional groups, or
No, not really a class like the others.
just extra?
They're just 2 additional ones. That's probably why they didn't end up in this table, because they're sort of maybe not following the class. But there are a couple here. Yeah, thanks. Phenol, right here. You don't want to call this an alcohol. When the hydroxyl group is on aromatic ring, it's best to call it a phenol. It's like a phenol with an alcohol, OL. It's a special type of alcohol. And the amine binds to the benzene ring. You'd rather not call it an amine. It's better to call it an aniline. It ends in ene. Nobody says aniline, though. I'm sure somebody does. Instead of saying aniline, it's called aniline. Okay? Aminobenzene. Anilines and phenols, a couple there. Other questions about functional groups? Common drugs. See any functional groups in Flavics? Flavics. Isn't that a commercial somewhere? No, commercial. What functional groups do you see in Flavics? How many aromatic rings in Flavics? How many aromatic rings in Flavix? Flavix has 2 aromatic rings, right? What's an aromatic ring? Every atom in the ring has a p orbital. Okay? All right. We'll be looking at that tomorrow. Functional groups in Flavix? Functional groups? Not thiol. Thiol is SH. Sulfide. Yes, you can call that a sulfide or thioether. Any other? Amine? What type of amine? Who said that? Tertiary amine? There's one big, the biggest, most prominent functional group, to me, it's not been named yet. The one that contains a carbonyl group? Yes. Ester. Yeah? Aryl halide? Okay. There's plenty in the plenty for practice around the warm-up sheet. Okay. How we doing? How we doing? DQ page. Formulas. DUS. Fluid structure. I think we're ready to start with Roman numeral 4 tomorrow. Yeah? A little bit of 3. Okay, guys? Everybody good?